Hello everybody, I hope you're doing well. Welcome back to another video in our Introduction to Calculus playlist. So, first things first, of course, Happy New Year. I know it's January 2nd right now, but Happy New Year to everybody. Hopefully 2023 is a superb year for all of you and hope for only good things to happen to you. So, with that being said, now that it's 2023 and we are in the Introduction to Calculus playlist, I think it makes sense to continue in the playlist. So, as you may recall, in the previous video, we have gone over the definition of the derivative, and we've gone through a toy example of how we can use the definition of the derivative to kind of find the value of instantaneous rates of change at given points. So the example we did in the previous video was the instantaneous rate of change of f of x equals x squared at x equals 1. We essentially constructed a table of points and used those points to kind of take the slope of, you know, lines at where the line starts to become more and more tangent. And from there, we were able to get an estimate for the instantaneous rate of change of f of x equals x squared at x equals 1. Now, in case you're wondering, you might be asking, okay, Karthik, we were able to go through a table and get the instantaneous rate of change, but I feel like that tool kind of seems tedious. What do we do? And the answer to that will be kind of revealed in the later videos. So stay tuned for that so that you can at least have a way of finding these instantaneous rates of change in a very easy and systematic manner. But now that we've wrapped our head around the intuition of the derivative, I think one thing that's good to point out is what are the limitations of our mechanism we have to define the derivative. So recall that we have set up this limit, right? The limit as x approaches c of f of x minus f of c over x minus c approaches the derivative, right, of f of x at x equals c. So we've talked about this limit definition, but one thing you might ask is, okay, so we have this limit definition. That's great. We can find the derivatives, but aren't there limitations to the tool that we have here? And the answer is yes, we have limitations of the tools. In fact, I'd like to title this video more of derivative gotchas because you might think that this limit definition is going to be like, the savior for finding the derivative, but there's actually a couple gotchas we need to watch out for, and we're going to dive into those cases in this video. So the first edge case we're going to dive into with regards to the derivative is considering the following case, right? What if we have discontinuity? So think about how in like one of the beginning videos in this playlist, we covered different types of discontinuity. So we've covered the idea of removable discontinuity, which looks something like this. So if we were to take derivative at this point right here, right? Well, this point is technically not defined in our original function, so we really can't use this limit definition, right? Think about what would happen, right? This f of c would be undefined, and if f of c is undefined, that means this removable discontinuous function can't exist at x equals c, so we really can't find the derivative for the case of removable discontinuity. We can also consider the case of infinite discontinuity. So we have a function that looks like this, and we want to say what is the derivative at x equals 0. Well, we can't really find a value for this function right here at x equals 0 because we have a vertical asymptote right here at x equals 0. So again, this f of c term is going to be undefined, or we can't compute it. So we can't really do anything with the derivative for points that are discontinuous in the case of infinite discontinuity. And the other type of discontinuity we covered was the idea of jump discontinuity. So if we had a function that was, behaving something like that, right? If we looked at this point right here, right? This is the point of jump discontinuity. We can't take the derivative right here, right? Because f of c, again, is going to be undefined, right? And thus, this limit definition won't work. And because this limit definition won't work, right? We can't take the derivative for the case of jump discontinuity at those locations. So discontinuity is a gotcha, right, that you might have been expecting with the derivative tool that we've developed in the past two videos. So hopefully case one is pretty straightforward. The second case we're going to consider is sharp turns. And the good example for this is actually a function you might be familiar with. Let's consider this function for example, right? Let's say we have f of x equals the absolute value of x. What does this function look like? Well, when x is positive, right, the function is going to output itself, right? So in fact, the absolute value, as you know, always returns a positive version of the number. So 1, 1 will be a point, 2, 2 will be a point, negative 1, 1 will be a point, and so on and so forth. In fact, the graph looks like this iconic V shape, right? Now, what if I asked you, right, find the derivative at x equals 0. So if you look at this function, right, let's try attempting to find the derivative at x equals 0. So we'll mark this point here in green, and we're going to use our definition, right? Limit as x approaches 0 of f of x minus f of 0 over x minus 0. But what is f of 0? This is just going to be 0. So that's going to be this. So this is going to be the limit as x approaches 0 of f of x over x. So this is going to be our definition, right? Now, think about the case where x approaches 0, right? From the positive side or from the negative side, right? So if we look at this point here, right? Let's say we repeat the exercise we did in the last video and took a table of points. Let's say we took a table of points that were using values to the right of 0. So let's say we had, yeah, sorry, I'm just changing the marker color. So let's say we had this point right here, and we want to take its derivative. So the slope of this line would be, this line here shown in green. And in fact, that slope is going to be 1, right? Because if you think about it, right, for any point where x is greater than or equal to 0 and f of x equals absolute value of x, you're just going to have a line y equals x, and the slope of that's going to be 1. And imagine bringing this point closer and closer and closer, right? You're still going to have this line right here, right, which is of slope 1. But the problem comes if you repeat that exercise, but you look at points to the left of x equals 0. So what if you consider this point here, negative 2, comma 2, and we take the slope of this line, right, between negative 2, comma 2 and 0, 0. Well, the slope of that line is going to be negative 1, and we move this point, negative 2, comma 2, closer and closer and closer, right? The slope here is still going to be negative 1, and the slope here is going to still be negative 1. You can test all this by plugging into the limit. But what you'll find is that when we're using, points to the left of 0, so x greater than 0, you're getting a slope as 1, right? The slope will approach negative 1, but when x is greater than 0, the slope approaches positive 1. And the problem happens where when you're approaching x equals 0 from the right-hand side, your slope is approaching positive 1, but from the left-hand side, your slope is going to approach negative 1. But that means that your slopes are going to be approaching two different values at x equals 0. So we don't have a concrete value for this derivative or this instantaneous rate of change. So hence, this is the case of the sharp turn. And thus, at x equals 0, you cannot differentiate f of x equals absolute value of x, or you can't find the instantaneous rate of change at x equals 0 for this function. So this is what I mean by the sharp turns and pointy aspects for some functions. So hopefully that makes sense with case number 2. The last case we're going to consider for gotchas with derivatives is this one. What if we had a case where we had a vertically approaching tangent line? So what do I mean by that? Here, let's draw an example of such a function. So one function we can consider is this function right here. Consider the following function. F of x equals the cube root of x. So what is that function going to look like? So let's draw a graph. So at 0, 0, you're going to have, the cube root of 0, 0. And then let's mark your axes. Okay, I'm marking our y values here. So the cube root of 1 is going to be positive 1. The cube root of negative 1 is going to be negative 1. The cube root of 8 is going to be positive 2. And the cube root of negative 8 is going to be negative 2. So if we draw the graph, it's going to look something like that. This is like kind of a very rough drawing, but hopefully you get the idea of what the progression looks like. Now let's consider what happens when we take the derivative, right? Take instantaneous rate of change at x equals 0. So how are we going to do this? Well, let's consider like a second point of interest and move the second point closer and closer to the x equals 0. And we're going to consider both cases. So I'm going to change this color to blue. And I'm going to say the second point is here, right? So what will be the slope between this point x equals 0 and this point right here? It's going to look more like that, right? But let's move this blue point closer and closer. So let's move the blue point here. So your slope is going to look more like that, right? The slope of the line. But when we move this blue point closer and closer to 0, right? You see the line is becoming more and more steeper, right? And in fact, if you move this blue point very, 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 very close, your line is going to become like super, super steep, right? It's becoming pretty close to vertical. And what if we consider the other case where we take a green point and let's say the green point was to the left of x equals 0, and we take the slope between the green point and this x equals 0 point. So the line would look something like this, right? So you'll have the slope. And then we move the green point a little bit closer. And then you take the slope between the green point and this blue point right here. And we move this green point really close right here. It's cutting close. And then the line's going to look something like that. And in fact, if we move this green point right almost infinitesimally close to this blue point, your slope is going to look, something like this very vertical line right here. So your tangent line, right? In fact, right? Like we discovered in the previous video, we've talked about the idea of derivatives as, or instantaneous rates of change as basically finding the slope of the tangent line, right? But at x equals 0, your tangent line is going to look very vertical, right? So tangent line becomes vertical at x equals 0. But think about like back to basic algebra, right? What is the slope of a vertical line? Well, a vertical line is one that has an undefined slope. So because our tangent line is going to become a vertical line at x equals 0 for this function f of x equals cube root of x at x equals 0, the tangent line will become vertical at x equals 0. And vertical lines have an undefined slope. So if the tangent line has an undefined slope for this case, right, then we don't really have a value for the instantaneous rate of change of f of x equals cube root of x at x equals 0. And hence, the derivative will be undefined for cases of vertically approaching tangent line. So that's a wrap for this video in terms of what are the major gotchas to know when computing instantaneous rates of change. And hopefully this video kind of helps you get a good feel for what are the limitations of the definition we came up with or the method we saw in the previous two videos for finding instantaneous rates of change. And in the next video, we will be starting to go through some properties of derivatives and coming up with a better system in order to compute derivatives with much more ease instead of making a table for every single scenario. So, as usual, don't forget to like and subscribe, and I will catch you in the next video.